the open box problem is really almost the perfect problem to work on. So we have a rectangular piece of cardboard. And it's 8 by 15. And what we're going to do is cut squares out of each corner. And what that will leave is something that can be folded along these dotted lines up to make a box, an open box with no top. Can you see how that would happen?
Yes.
Okay. And the idea is, what should that measurement be such that I maximize the volume of the box? And you can see that that would be a very important real-life problem. In other words, if you were in the business of making boxes, you would want to make the maximum volume for the least amount of cardboard, right?
Yes.
Okay. So the way you do this problem is, first of all, by defining the formula that you want to maximize. Well, we want to maximize the volume. What's the formula for the volume of this box? What's the general formula for the volume of any box?
Length times width times height.
Okay. In this particular box, what's the length measurement?
Length would be 15 minus 2x.
Okay. And the width?
Would be 8 minus 2x.
And the height?
Would be 8. Or sorry, x. My bad.
Okay. Notice what that gives us. That gives us a cubic. Okay. In other words, if we do the multiplication, we will have a cubic function. And a cubic function looks kind of like this. Okay. And right there is going to be where a local maximum occurs. Right there is going to be a local minimum. I might not have drawn it quite right. It might look more like that. No, use this first picture. Okay. If I multiply these three terms together, let's go ahead and do that, because we're going to have to do it at some point. Are you comfortable how to do that? You want me to just go ahead and do it real quick to save time?
Yeah, that would help.
120 minus 30x minus 16x plus 4x squared. Then we're going to multiply that by x. So let's put the leading term first. That's going to be 4x cubed. And then let's see, we have a total of minus 48x. So that's going to be minus 48x squared. And finally, we have plus 120x. So that's our volume as a function of x. So, I mean, before calculus, we would just try a whole bunch of different x's, and whichever one came close to producing the biggest volume, that's the one we would choose. But from a mathematical perspective, we can find the exact x that produces the maximum volume. If my volume function, there's one other thing here we have to consider, and that is our effective domain. Let's look at our problem again. what's the effective domain for x? We know x has to be greater than 0, otherwise you wouldn't have a box, right? In other words,
Right, and less than 8.
x is 0, volume would be 0. But what's the upper end? Obviously, x can't be 4 either, because
Oh, yeah.
if I made x 4, I would have a suitcase that had no volume also. So it's got to be between 0 and 4. Okay? You with me?
Okay.
All right.
Yes.
Now, if we go back and if I had time, I would pull this up on Wolfram Alpha so we could look at it. But I'm going to pretend here that that's 4 and that's 0. Well, notice, and this is v of x right here. Okay? Notice these local extrema. You've learned a lot about local extrema. The most important thing you've learned is that they have slopes of the tangent line that are 0. So whenever you find a slope of the tangent line, which is the same thing as first derivative, that is 0, you know you're looking usually, not 100% of the time, and I'll teach you how to differentiate that, but most of the time you're looking at either a local maximum or a local minimum, as is the case here. Okay? Well, the question is what is that value on the x-coordinate? Because that's the value we want. That is where our volume is going to be the highest. Now you might say, well, over here the volume is higher, but that's outside of our effective domain. Remember, our domain is only between 0 and 4.
Yes.
Okay, so what we're going to do is down here, we're going to take the first derivative, v prime of x, which is what?
V prime of x would be 12x squared minus, what's...
90.
Yeah, 96x plus 120.
Okay, and now what we're going to do is find out where the first derivative is 0, right? In other words, if I set that equal to 0, the points I'm going to find are that one and that one. And then it's all we have to do is figure out which one's the maximum and which one's the minimum. And of course, we'll be looking for the maximum. So I set that, and first thing I can do to this function to break it down a little bit is divide everything by 12, right? In other words, if I factor out a 12, I'm left with x squared minus 8x plus 10. Really, they give us one that doesn't factor nicely. Come on. Calculus is hard enough. Why don't they give us one that has an easy factoring? They're going to make us use the quadratic formula. Okay? First thing, which is all right, we'll do it. But first thing is I can divide both sides by that 12, so that 12 is not a factor anymore. Okay? So now I have a simple quadratic formula that I have to solve for x, and it's going to give me two solutions, because quadratics always give you two solutions. And one of them is going to be this first circle, and the other one's going to be the second one. Okay, so let me do this real quick. X equal minus b plus or minus the square root of b squared minus 4ac all over 2. That is 8 plus or minus the square root of 24 all over 2. Square root of 24 can be written as square root of 4 times square root of 6, which can be written as 2 square root of 6 all over 2. And now I have my two answers, a plus or minus square root of 6. Okay?
All right.
Both of those are positive numbers. Square root of 6 is approximately 2.5 maybe. So I get two positive numbers.
Okay, and they're both less than 4.
Correct. Well, no, the second one is not, is it? The plus is greater than 4. Thank you for
right. Yeah.
Thank you for pointing that out. Therefore, that's not one of the answers. The only answer
So it has to be 4 minus.
4 minus root 6. And if I go up to my curve, what that means, I haven't drawn this properly because I was just estimating it. But if this is 4 minus root 6, that point is what produces a maximum volume. Now, what are the dimensions of the box of largest volume and what is its volume? Well, we just figured out what the dimensions are because we figured out what x should be. X should be 4 minus root 6. So if we go back up to our box, we know the dimensions of the box, right? I mean, this is 15 minus 2x, that's 8 minus 2x. So if I label this box, this is going to be 15 minus 2x is going to be the base of the dotted line. And this is going to be 8 minus 2x. We know what x is. We know what the dimensions of the box are. All right? Now, to figure out what its volume actually is, well, we figure out what V, the original volume formula, V of 4 minus root 6. And you solve that by plugging 4 minus root 6 in for x and coming up with whatever the volume would be.
All right, gotcha.
Okay?
Good deal.
And this is kind of the easiest case problem for optimizing. And that's why I like to start on it. Because it really only involves one function, and that's a volume function.
Yeah.
Okay? All right, let's go up and look at number 6. Do you have to do 6 also?
No, we had to just do the odd numbers.
Oh, just the odd numbers, okay. So let's do 9.
Okay.
So here is the picture for 9. You have a rectangular piece of land that's bordered on one side by a river, okay? And you're going to use it for livestock, but you don't have to put a fence on the riverside, right? In other words, the livestock can go up to the river. And the question is, you have 800 meters of wire at your disposal. How can you design this rectangular plot of land so that you get the maximum area? Okay? Well, like any good word problem, we need to put some variables. Well, let's call this x, the horizontal distance, and let's call this y, and that's clearly y also. So when you're doing these optimization problems, the very first thing you really want to do is figure out what you're trying to optimize. Well, we're trying to optimize area. What's the area of that shape?
It's 2x, oh wait, so x times y.
Okay. Now, notice what I have now. My area function is a function of two different variables. Well, I can't find anything out by differentiating this because I got two variables. So I need to turn my main formula into a formula of one variable. Well, the other information they gave us is that we have 800 meters of wire. What's the perimeter of this area?
So it would be 800. So you'd solve for either x or y.
No, hold on. Just define the formula for the perimeter of that three-sided rectangle.
It would be x plus 2y.
Now, there's a second equation that's going to let me define x in terms of y. Or vice versa. It doesn't really matter. You'll see why. So I'm going to have x equals 800 minus 2y, right?
Yes.
Now I'm going to go back to my important function, the one I'm going to try to maximize, and I'm going to turn it into a function completely of y by substituting for x, 800 minus, you know what, let's make this all an x. I risk confusing you by using y. Let's solve that for y instead of solving it for x. You'll see why.
Okay.
So y is equal to 800 minus x over 2. Okay? Now, when I go to my area function, instead of y, I'm going to write 800 minus x over 2. So I have x times 800 minus x over 2. And that is a function. Now I have my area function as a function of x only. That's a good thing because this I can see as a quadratic, okay? And I can also see that it's a quadratic that opens, a quadratic is a parabola, and it's going to open down. Hold on 1 second. Hello? Yeah, Leslie, listen, I'm in a session. Can I call you back in 10 minutes? I need to talk to you about Jacob's sessions tonight. I'll get back to you in 10 minutes. Bye-bye. All right. Sorry about that. I am booked solid, and I'm trying to wiggle and gain an extra half hour somewhere.
Gotcha.
If I take my area function and were to graph it, I can see I'm going to have a minus x squared, right? That tells me I have a parabola that opens down. Well, where's the maximum area occur? Right there. Okay? In other words, what is going on there? The slope of the tangent line is 0. So, and the value I'm going to find is that value right there. That's x, that's a of x. So I want to find this. Now, we don't need calculus to find the vertex of a parabola. We know how to do that. But notice that the moment our function gets beyond quadratic, like the previous problem was a cubic, we don't have geometry to find that. We need calculus for that. And when you get functions that are even more complicated, finding where the first derivative equals 0 is hard to do without calculus. So we're going to apply calculus to this anyway. So my area function ends up being 800x minus x squared over 2. I guess that's 400x. So 400x minus x squared over 2. That's our area function. Differentiate that. What do you get? A prime of x
A prime of x equals 400 low d high.
What's the derivative of that?
It would be 2x. Oh no.
Go ahead. No, that's the way to do these. Start with the exponent immediately. Put it down in front and subtract 1 from it. That gives you minus 2x over 2, or minus x.
Right. Okay.
Okay? Now, we know the point we're looking for is where a prime of x equals 0. Well, that tells me exactly where it is. It's when x equals 400. Okay?
Okay.
That means if I go up to my picture, this is 400. Got 800 worth of wire, so the y's are 200 each. And that's the shape of my rectangle that gives me the maximum volume. And if I want, or the maximum area, excuse me. And if I want that area, it's 200 times 400, or 80,000.
Okay. Cool.
And this was just slightly harder than the previous problem because this involved 2 formulas. And most of the time you do have 2 formulas. You have your primary formula, which is the one you're trying to maximize, and then you have some secondary formula that allows you to state the primary formula in terms of one variable only.
Mm-hmm.
Okay?
Okay.
But your primary formula usually starts out as a function of 2 variables. You can't do anything with calculus with 2 variables. You got to get it down to 1 variable. So having this information about what the perimeter of the fence was allowed us to define y in terms of x, and that allowed us to then take our area function and differentiate it and solve and find out where the first derivative was equal to 0.
All right. Understood.
Okay, let's see. We got probably time for one more. Let me go to 11. I assume 11's going
I
to...
don't know if 11's on there. I sort of jumped around.
Which page would you like to go to for our last 5 minutes here?
Well, what we did last night was the graph problem, so 37.
I can't see which one's 37. We're talking lower?
Top right.
Top right, okay.
We just, we don't have to do all parts. We just have to do pretty much A.
Okay. This is another classic problem for calculus. What's the general formula, the strength for strength? According to their first sentence.
S equals WD squared.
Yeah, because it's proportional to the width times the square of its depth. So that's width times the square of its depth. And actually, when it says it's proportional, there's some k there. Also.
Oh, okay.
Okay? That k will go away as we do the problem, I believe. So find the dimensions of the strongest beam that can be cut from a 12-inch diameter cylindrical log. The circle is if you cut a log right across the face, you'd be looking at that. Okay? So they're trying to figure out what is the best shape to use to cut this wood so that we have the strongest beam. In other words, where S is a maximum.
Okay, great.
All right, so if we look at this picture down here, we need a second equation, right? Because right now, K is a constant, but S is a function of W and D.
And you can find D squared.
Well, you can find D as a function of W by using this triangle here. That triangle is W squared plus D squared equals 12 squared, or 144.
Yeah.
Okay? So it doesn't matter which variable we solve for, W or D. So I'm going to just automatically solve for W here. So W is going to be the square root, actually the plus or minus square root of 144 minus D squared, right?
Okay.
Clearly I don't want the negative answer. Dimensions are always positive. So let me erase the negative. In other words, it's
Well, do you even need to do that? Because you could just plug in D squared. So 144 minus W squared.
yeah, but when you're doing the math here, W is equal to plus or minus this. But we know W has to be positive. So the minus I can throw out as a potential answer.
Right, but if you solve for D squared, wouldn't that be easier?
No, hold on. No, it's going to be just as hard to solve for either one. You'll see.
Okay.
Now we're going to go into our strength formula. And in place of W, I'm going to put this. Square root of 144 minus D squared times D squared. There's our new strength formula, and it is a function of D. So now by working with this formula, I'm going to be able to solve for D. What D will give us the strongest log that we can cut from this circular log? That's what we're going to determine.
Okay.
Okay? And the way you're going to do this is I'm going to have to cut this short, but we're going to take the derivative. That's almost always the first step, incidentally. In other words, once you get a function defined in terms of one variable, then the next step is always to take the derivative. And then set it equal to 0. Because where the derivative equals 0 means the slope of the tangent line is 0, and that happens when you get maximums and minimums.
Right. Okay.
So once you take the derivative of that and set it equal to 0, you're going to be able to solve for D. That K is going to, you're going to be able to divide both sides by that K. So effectively that K is not a
That'll just cancel
let's
out.
even take it out of there. It's kind of like that,
Yeah.
that 12 that was in front of the other problem. We could just divide both sides by it and get rid of it. So you need to take the derivative of this, which is not that easy. In other words, you're going to have to apply the product rule and the chain rule to take the derivative of this. It's going to be fairly complicated. And then you're going to set it equal to 0 and have to solve for D.
Okay.
And that will be your answer. In other words, once you solve for D, now you can go back up into this equation and solve for W.
So it's always the same process. So you sort of like have this model.
It's the same process. You define your function that represents the one you're trying to optimize.
Okay. Then you find the critical points and then you solve for it.
Second function that allows you to take one variable and define it in terms of another.
Yeah.
Oh, okay. They did have a K in here. Yeah. I shouldn't have erased that. There is a K there. It will divide itself out, but let's not erase it yet there. Let's put it back because I'm just looking at B and C here. They're talking about the K.
Okay.
But once I take the derivative of this and set it equal to 0, that K, I can divide both sides by K and it'll disappear for the purposes of determining the D that gives us the maximum strength. Notice we're not looking for the maximum area here. We're looking for the maximum strength. This is the strength function. So a bigger D relative to W is clearly going to make a difference because D is being squared. So if you have a big D and a small W, you get a lot of strength. If you had the same W as D, in other words, if I cut a square out of that, that clearly would not give you the most strength. the
Right.
measurement is much more critical to your strength than the W is, because it's being squared. So anyway, this allows you to figure out those answers. I don't know about B and C, but certainly A can be answered using this same exact technique.
Okie dokie.
Okay? Do you happen to know what time your brother gets home from school, or when he'll be home today?
I'm not quite sure.
Okay. I'm trying to jiggle his schedule around by 15 minutes perhaps, one way or the other. I'll give him a call. I'm pretty sure I have his number. So, all right, Matthew. Well, good luck with this. This is where calculus starts getting hard. And what follows this is related rates, which is even tougher. Well, not tougher, about the same toughness, I would say.
Okay.
All right.
Well, thanks so much.
Talk to you next time. Bye-bye.